Welcome to this video about the curl operator in vector fields. The curl is a fundamental concept in vector calculus that helps us understand how a vector field rotates at different points in space. Before we dive into the mathematical definition, let's try to understand the curl intuitively. Imagine placing a small paddle wheel in a flowing fluid represented by a vector field. If the paddle wheel rotates, there's a non-zero curl at that point. The faster it rotates, the larger the magnitude of the curl. The axis of rotation gives us the direction of the curl vector. Now let's move on to the formal mathematical definition of curl. For a three-dimensional vector field f with components f_x, f_y, and f_z, the curl is defined as the cross product of the del operator with the vector field. In Cartesian coordinates, it can be written out explicitly as shown here. To better understand this, let's consider a simple two-dimensional vector field, given by f equals the vector with components -y and x. This is a rotational field, where vectors rotate counterclockwise around the origin. Let's calculate the curl of this vector field. Since we're in two dimensions, we can treat this as a three-dimensional field where f_z is 0 and all partial derivatives with respect to z are 0. This means the curl will have components. For the x component, partial of f_z with respect to y minus partial of f_y with respect to z. Since f_z is 0 and derivatives with respect to z are 0, this becomes 0. For the y component, partial of f_x with respect to z minus partial of f_z with respect to x. Since f_z is 0 and derivatives with respect to z are 0, this becomes 0. For the z component, partial of f_y with respect to x minus partial of f_x with respect to y. That's the partial of x with respect to x, minus the partial of -y with respect to y. This gives us 1 plus 1, which equals 2. So the curl of our vector field is a constant vector pointing in the z direction with magnitude 2. This makes intuitive sense because our field rotates counterclockwise around the z-axis with the same intensity everywhere. Now, let's consider a different example. Let's look at a radial field given by f equals the vector with components x and y. In this field, all vectors point outward from the origin, with magnitude increasing with distance. Let's calculate the curl of this radial field. Following the same process as before, the z component of the curl is partial of f_y with respect to x minus partial of f_x with respect to y. That's the partial of y with respect to x, minus the partial of x with respect to y. This gives us 0 minus 0, which equals 0. So the curl of this radial field is 0 everywhere, meaning it's an irrotational field. If you placed a paddle wheel anywhere in this field, it wouldn't rotate. Let's connect the curl to a physical interpretation. In fluid dynamics, the curl of the velocity field represents the vorticity, or local rotation, of the fluid. The curl also appears in Stokes' theorem, which relates the surface integral of the curl over a surface to the line integral of the vector field around the boundary of that surface. In conclusion, the curl of a vector field measures the tendency for the field to rotate around a point. It's a vector quantity whose direction gives the axis of rotation, and whose magnitude indicates the strength of rotation. For a vector field to be conservative, derivable from a potential function, its curl must be 0 everywhere. This property is important in physics for fields like the electrostatic field and gravitational field. I hope this video has helped you understand the curl operator both mathematically and intuitively. Remember, whenever you're analyzing a vector field, the curl is a powerful tool for understanding its rotational behavior.